Now we're moving on to variable length subnet masking and route summarization. The problem with all the scenarios we've seen up until this point is that we've been using the address space inefficiently. As you saw in the Class C situations, we would have to use up whole ranges of addresses just to make a point-to-point connection. So it's a very inefficient use of the subnetting or IP address range. And it isn't typically used. In the real world, we use variable length subnet masking, this flexible concept that allows us to move around through the bits depending on the size of the network. They don't have to be based on sequential blocks of IP addresses. And then we're going to talk about route summarization. When we have all these routes, we want to take all these routes. If we have 10, 20 routes that fall within the same block ranges, we can take all those addresses and summarize them as one route out to the external networks, thereby just making our routing tables more efficient. Less routes that we have to propagate throughout the network, the more efficient the routers are. So let's take a look first at variable length subnet masking. So here I have a Class C address, and we're going to walk through a couple of scenarios subnetting a Class C, but not in the traditional way. In the traditional way, we would have to select a particular bit. We would draw a line down that bit, for instance 16, and then our networks would go in increments of 16. If we had a particular network that required 30 hosts, we couldn't do it. We would have to break that up into two networks to accomplish it. Very inefficient. What we want to be able to do is build our networks based on our host needs and then be able to move around through the bits as we need them and borrow bits as we see fit. So what I'm going to do is draw out a little scenario, and then I'm going to walk you through figuring out how to address it using variable length subnet masking. So let's connect our networks together. So we'll connect router 1 to router 2. I'll just make it a straight line. So we have our routers connected, and then we're going to draw a couple of network segments. And what we're going to say is that we have a network segment over here, and one over here, and we have one down here. The difference is going to be is that on LAN 1 over here, we require that we have 100 hosts on this network. And on LAN 2, we're going to say we need 50 hosts over here. And on LAN 3, we need 25 hosts. Now that would be a problem with traditional subnetting, because first of all, we would look right over here and realize that, hey, we have to draw our line here, right? And then we're only going to have two networks, but we have 5 networks. We have 1, 2, 3, and don't forget about these, 4 and 5. So that's not going to work. But variable length subnet masking allows us to configure an IP scheme that's flexible enough to work with this type of a network setup. The key with variable length subnet masking, there's 2 rules that you have to steadfastly follow. Well, I should say you don't have to follow these rules steadfastly, but they will make variable length subnet masking much, much easier for you. The first rule is, when we've been subnetting in the past, we've always looked at how many networks do I need. So I would assess this by how many networks with standard subnetting. When you're dealing with VLMS, SM, variable length subnet masking, when you're dealing with variable length subnet masking, you don't worry about the LANs necessarily initially. You're concentrating on how many hosts you need on each segment and the connections between them. So let's take a look. It's a little bit different way of looking at things. So let's take a look at that. Protecting hosts, that's what we're after right now. We have to protect enough bits for 100 hosts over here, 50 hosts over here, 25 here, and then 2 point-to-point connections. Instead of thinking about the network and borrowing bits from high order to low order, what we've been doing with regular subnetting, we're not going to do that here. We're going to think about how many bits do I have to protect to get that number of hosts on that network. The other rule is, besides protecting the host bits, is always start with the largest network first. You don't have to. That's not a concrete rule. You'll see situations and examples where they do not choose to start where the largest block of users first. As a matter of fact, there are more efficient ways of doing it, but they are much more complex to learn. And in the beginning, as everything else with IP addressing, you have to take the steps to move forward. This is variable length subnet masking. This is one way to do it. This is the easiest way to understand the concepts. So my rule is, in my class, is start with the largest network first and then work your way down. So for this instance, we have 100 users over here, 50 users over here, 25 users here, and then 2 and 2 point-to-point connections. We're going to start with LAN 1. And we ask ourselves the question, how many bits do I need for 100 hosts? Well, remember, when you're counting host for host, you're always going from low order to high order, right to left. So I have 2, 4, 8, 16, 32, 64, 128. Stop. That's enough bits. Those 7 bits will be enough for that network. I'm going to draw my line. Line goes down the middle. And from this point, once we've figured that out, once we start with the largest network and then figure out the number of hosts number of host bits that we need to protect, it goes right back to the way we've always done it. All right, we go right back to the way we've always done it, and we look at how many bits do we have in the network portion? 1, which means we're going to have 2 networks. They're going to go in increments of 128, starting with 0. Right? Nothing has changed, so I have 0 and 128. I know that the number before this network is going to be the broadcast, so I'll just write out 0 to 127, which means the host addresses, of course, are going to be 1 to 126. I'm going to assign that address, that network address over here. So I'll assign 192.168.10.0 with a /25 mask, right? We have to put the mask down, of course. So I have a /25 mask. Done. I have now allocated the correct number of IP addresses for this network. As a matter of fact, we have a little bit to spare. Perfect. So now we look at our next network. We're going to get rid of this. And I'll leave that there because we can see it's 50, so that means we're going to have to go to the 6th bit, right? So we're going to be protecting host all the way to the bit with the value of 32, and then I'm going to draw a line down here, and my network's going to go in increments of 64. Now here's another rule. 3 rules. That's the only 3 you have to remember. Start with the largest network. Always protect the host bits. Don't worry about network portions right now. You're protecting host bits. And the other rule is, and this is an important one, never reuse an IP address range. What I mean by that is we've already used 0 to 127. We've used the 0 network all the way up to 127, so we cannot use that to address this block of 50 users. So how do we do it? Easy. We know that 0 is no longer good. Well, we're going to go in increments of 64. 64, 128, stop. This network segment over here was 0 to 127. So that means we can't, if we were to write out the numbers that are here, 0 to 63, 64 to 127, these numbers are gone. We can't use them. We address them over here. So we have to start from this point, from the 128 network, and go in increment of 64, which would make it 192. So we can use this number, 128 to 191, to address LAN 2. And that's what we're going to do. We're going to assign the number 192.168.10.128 with a mask what? A /26 mask. Now we cross those numbers off too, because they're gone. You're starting to see the logic behind this. Right? Just cross over the numbers that you've used as you use them and go in the increments that you need to for your particular network. So once again, we're looking at LAN 3 down here. We're going to get rid of that line. We can easily see it's going to have to be in blocks of 32. We're going to need at least 32 users or 32 possibilities to fulfill that 25. I'll draw my line. Draw my line down there. I'll get rid of that little arrow because we know that part already. So we know we're going this way. We're going in increments of 32, so we could write it out 0, 32, 64, right? And we would go all the way down to 192. So from here, we just add 32 to 192, and we end up at 224. Remember, I always define the next network because it makes it so easy to see the range of the network I'm working on. Number before that, 223, we know 192 to 223 is the network range that we have available. We're going to assign the 192 network number down here. So 192.168.10.192 with a slash what? A /27. See, it's not difficult at all as long as you follow those 3 rules. Protect host bits, start with the largest network, work your way down to the smallest, and never reuse a range. Okay, we're done with this range. It's gone. We can never use those numbers. So we've used everything from 0 to 123. All those numbers have now been used. We still have to address these point-to-point connections. And this is the beauty of variable length subnet masking. Look what we're doing here. We could never have done this with regular subnetting. We would have gotten 2 networks, and then we would have had to use a different IP address scheme to fulfill these. And that's not possible when you're using public IP addresses. And then you have to create routes, and we still have to deal with the routes even with this scenario. But it just causes more overhead and more documentation. Okay, moving on. Let's go and address these point-to-point connections. Well, point-to-points only need 2 users, which means they're going to go in blocks of 4, right? Because we need 2 bits to get 2 users. Remember, in 2 bits we have 4 possibilities. We see that right there. Well, one's a network, one's broadcast, which means we only have 2 hosts. Well, that's exactly what we need. So that tells us that our network's going to go in increments of 4. All right, we're going to borrow that right to there, draw our line. So our networks are going to go in increments of 4, because we're looking at the number down here, not those numbers up there. Let me get rid of those numbers up there, because those numbers represent the number of possibilities. The increments it's going in is right down here. So we're going in increments of 4. Well, let's start from 224. That's the next network, right? So we just start, and we go 224 on top of 224 is 228, and then 232, and stop. Now we just fill out the range. That'll go to 227, and that'll go to 231. So you should be saying to yourself that the addresses, right, the interfaces here and here, if I assign the .24 network to it, are going to be .25, .225, and .226. And the network for here will be 192.168.10.224. The next network, they're gone, right? We can't use them. Next network is the 228 network, and we're going to assign it over here, 192.168.10.228. We'll assign the addresses in between, so it's going to be .227 and .230. I'm sorry, 229, not 227, and .230. Look at what we've done. We've assigned 100 users over here, 50 users over here, 25 users over here. We've done point-to-point connections, and we still have addresses left. We still can go from 32 to 255, right? That's the broadcast for the last network, but we still have the possibility of throwing another network out there if we need to. So that's variable length subnet masking, a Class C style. One, two, three, four, five, six segments, network segments that we have to deal with. We're going to say that this one over here requires 65 hosts. This one over here requires 10, and this one over here requires 40. So now, once again, we follow our rules. What's the rule? First rule is we're protecting host bits, not worrying about networks. We're going to start with the largest network first, which is LAN 1 over here. So 65 users, how many bits do I have to protect to get to 65? So 2, 4, 8, 16, 32, 64. I draw my line right here. My networks are going to go in increments of 64, starting with 0. So I'll start with 0, 0, 64. That's good enough for that one. 0 to 63 will work. I'll take that number and plug it in right over here. 192.168.10.0/26. Next network is down here. It's the 40. So we need 40 users. Well, how many bits do we need for 40 users? So 2, 4, 8, 16, 32, 64. Well, we're going to have to use it again. So we're going to use the next network segment. We're going to stick with the blocks of 64. So we're going to go to 128. We're going to say that the 64 to 127 will be applied or assigned to LAN 3 down here. So let's go ahead and put that in there. 192.168.10.64 with a /26. Now here's the thing. These are gone. We've assigned them. This block went to LAN 1, this block went to LAN 3. Now we're on to LAN 2, and we only need 10 users. So 2, 4, 8, 16. Draw our line. We found 4 bits is enough for 10 users. As a matter of fact, we'll end up with 14, a little room for growth. It's going to grow in increments of 16. So that would be 16 and 128 is 144. So we're at 144. Right, so that's enough right here. We can stop. So 143 is the network range. We're going to come over here and assign that number of 192.168.10.128 with a 25, 26, 27, 28 mask. With a 28 mask, and we're going to get rid of those numbers. The next we have to do is assign the point-to-point connections that we have here. So let's go ahead and do that. They're going to go in increments of 4. We already know that. All right, we know it's a /30. That's what we forgot to put down there before in the other example, by the way. So we know it's a /30, going to go in increments of 4, 2, 4. Draw our line. We're good to go. So we're at 144 going in increments of 4. So at 148 and 152 and 156. These are enough to address our networks. And we can just apply those IP address ranges to here. So we'll just use .144 for here, .148 for here, and .152. I'm just using the last octet in the range. Remember, that is a /30 mask. A /30 mask. So once again, we've assigned all the necessary IP addresses, fulfilled all the requirements on our network, and we still have IP addresses available for future growth. That is variable length subnet masking. Once again, as long as you remember the rules, you can variable length subnet mask any situation, and there's many practice examples for you in your pamphlet that was sent to you. So I encourage you to go ahead and do that. Now let's try our hand at using variable length subnet masking on a Class B address. The key to being successful with this is to use the methods that you used when you subnetted traditional subnetting of a Class B, and the methods you used when variable length subnet masking a Class C address. Combine those two together, and you'll see that subnetting a Class B address with variable length subnet masking is not that much more difficult. It just takes practice. Here we have our little network scenario, and I've set up a couple of network segments. We're going to have a lot of writing on the board, so I wanted to keep it a little clean. You'll notice that we now have router 1 with 1,000 hosts over here. So we have 1,000 hosts. The second route has 400, and the third router has 250 hosts. One of the things I find helpful to do before I start actually subnetting is to write out the powers of 2. Remember, everything is powers of 2. So it helps to have a little chart up on top so I can see how many bits I need to borrow for a particular number of hosts. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. And 2 to the 10th is 1024. What's nice about this is the exponent that you see here in the calculation is really the number of bits. We can use that exponent to identify the number of bits we need for a particular number of hosts. So it just makes it a little bit easier. Less chance of miscalculating something. We have our rules, and remember, do not be thrown by the fact that you're dealing with a Class B address. We're going to start out being focused right here in the third octet. That's going to be where we're going to focus our attention in the beginning. We go back to using the same methods we've used before, just use them on the Class B. What's the first rule? Or what's one of the 3 rules that we have, I should say? Start with the largest network first and protect host bits. Know that the host bits are going in this direction. We know host bits go in that direction from high order to low order, right to left. So we have to protect those bits. First network we're going to deal with, since it's the largest one, the largest network first to work our way down is 1,000 hosts. So how many bits do we need to protect for 1,000 hosts? Where we can look up at our chart here and we could see that we need 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to draw our line right there. Draw our line in between the 2 and the 4. So our networks are going to go in increments of 4. Right? So that number right there tells us what increments our networks are going to go in. Start over here. I'm going to go 0, 4. We can stop there. Now remember, we're dealing with the Class B. So we go back to what we know about Class B addresses. Best thing you can do at this point is define your range. Make it a little bit easier on yourself. So it's a 0 network. First host is going to be 0.1, and it's going to go all the way up to, next number is 3, 3.255. So I'm going to come over here, and we're going to plug that number in over here for the first network. And that number is going to be 172.16.0.0 with a slash what mask? 8 plus 8, 16, 17, 18, 19, 20, 21, 22, a slash 22 mask. Now we do it all over again, same way we were doing with the Class C address. Next network, 400 hosts. We ask ourselves, how many bits do we need for 400 hosts? We can look up at our chart here, and we can see that 2 to the 9th is 512. That's the number of bits we're going to need for 400 hosts. We'll just have room for growth, and that's always good. 9 bits, that brings us right to here. Draw our line. And our networks are going to go in increments of 2. 0, 2, 4. Remember, we can't use any of the numbers here. We've already allocated them. So we're just going to wipe that out so we don't even think about it. 0 and 2 is not available. We're going to start from 4. And our networks are going to go in increments of 2. So the next network number is going to be 6. And remember, we always define our next network because it shows us the range, clearly gives us the range of what we need. And in this case, the range is going to be 4.1 to, next number is 5, 5.255. We're going to come over here and we're going to apply that to this side. 172, 16, 4.0 with a slash what mask? A slash 23 mask. 8 plus 8, 16, 17, 18, 19, 20, 21, 22, 23. Great. Now we're going to get rid of those numbers because we don't ever want to use those again. Next thing we're going to do is look for our next network, which is 250 hosts. How many bits do we need? We look up at our chart. We see 2 to the 8th is 256. That's going to work. We need 8 bits. Right? We know that this last octet contains 8 bits. To draw our line in between the octets. This looks a little weird at first, but it's perfectly fine. So we'll just draw our line right down here. And what are our networks going to go in increments of? Remember, it's always the number. Don't let it throw you. Our networks are going to go in increments of 1. All right. Come back over here. Look at our chart. What's the next number? 7. So we define our network. It's going to go from 6.1 to 6.255. And that's the number that we put down here. 172, 116.6.0 with a /24 mask. And that is subnetting a class B with variable length subnet masking. As you can see, it's not much more difficult than doing a class C. Once you combine the subnetting of a class B and the variable length and the subnet masking of a class C. Combine those skills together and you can easily use variable length subnet masking with a class B. And I think if you were looking at this, you were wondering and asking yourself questions. Okay, Ed, that's great. We're in this octet and I understand that. What happens if we were to borrow network bits with a class B address and go into the 4th octet? How do we handle that? So that's what we're going to look at now. Our network has grown. Right down here we can see our network has grown. We have 100 hosts. So 100 hosts is going to force us into this 4th octet. Once again, don't let it throw you. It's not that difficult. Just follow your methods. So let's go ahead and do that. We ask ourselves the same questions as we have before, and let's just put up our little chart here. Well, how many bits do we need for 100 hosts? We have 100 hosts. We look up a little chart here and we see we need 7. 1, 2, 3, 4, 5, 6, 7. We're going to draw our line straight down here. At this point, I want you to just forget that you're dealing with a class B address. If this was a class C, you would know exactly what to do. You're going to look at this. You have 2 networks, and your networks are going to go in increments of 128. So let's just write it out as if it was a class C and not worry about the class B part just now. So we have the 0 network. We have the 0 network, and we have the 128 network. And the range is going to be 127 to 255. Right, there you go. If that was a class C network, that's what we would be using. But we're using a class B. We're going to add some more information over here and then see how we can plug those 2 things together. When we were at this point, we left that we had pretty much used all the network numbers up to the 7.2.16.6. So we know we can't use anything from 0.1 all the way up to 6.255. Those numbers are gone. We can't use those. What would be our next number after 6.255 is 7. We're going to use 7, and all we're going to do with 7 is there's going to actually be 2 network segments within that 7 number. We're going to have 7.1 to 7.127, and then we're going to have 7.128 to 7.255. We're going to take the first possibility within there, which is the 0 network, and we're going to plug it in over here. So 172.16.7.0 with a what type of mask? Well, we're over here, so we're going to actually have a /25. 8 plus 8 plus 8, 24, plus 1, 25. Now you say to yourself, well, what are we going to do with this network? We're not going to do anything with the 7.128. We're going to leave it. It's going to be reserved for a future date. So we're going to cross out that line right there. And then we're going to say that our network actually has grown some more. And so we're going to throw another network out here. and we're going to throw another 1,000 hosts on this network. So we've defined everything else, and all of a sudden now we have another 1,000. Well, how do we work that? Well, what's the next network number after 7? Well, it's going to be 8, because we're not going to use that one right there. We go back up to our method that we used up here. We look at our chart. How many bits do we need to borrow? We need to borrow 10 bits. So let's go draw our line. 8, 9, 10. Draw our line. Goes in there. Our networks are now going in increments of 4 again. Right, increments of 4. So 8, 12. Let's define the range here. It's going to be 8.1 to 11.255. We're going to plug that number in over here, which is going to be 172.16.8.0 with a /22 mask. Once again, we'll draw out, delete those numbers, and we're not going to use them. Notice this is still available, and it'll be available for growth later on. You don't have to use everything sequentially. You can leave a block of addresses available in the middle of the range that you haven't used yet. This is the beauty of variable length subnet masking. As our network grows, we'll just have a documentation indicating that this has been reserved, and we're starting at 12. And it doesn't matter from that point. We could add another network if we wanted to. We know we're going to start from 12. We're going to use the same method, find how many bits we need, and just go from there. So as you can see, using VLSM on a Class B address is not that much more difficult than using it on a Class C. Just have to use the methods that you've learned in the previous lectures, and then you'll do just fine. Next, we're going to be moving on to route summarization. This is where we take all of these IP addresses and these network ranges that we have here and summarize them to the external route as one route. Now let's talk about route summarization. Route summarization is also known as supernetting, aggregated addressing, and summary addressing. Any of those terms mean the same thing. What route summarization is the act of taking multiple network segments, as we see here, and summarizing their routes into one route that we advertise out to the rest of the network. Why would we do that? Well, first and foremost, it is an efficient way of using routers and routing tables. Think about it this way. We see 4 networks here in front of us, but what if we had 200 network segments behind that router? That router would have to know and keep track of 200 networks in its routing table and advertise that out to the rest of the network. Well, while that's perfectly fine, it also makes the router work much harder. Think of it this way. I have multiple phone numbers, cells, home, office, that you could contact me at. Well, I guess I could just, publish all those phone numbers and put them on my blog and send them out in emails and say, when you want to contact me, try to call these numbers. Well, a more efficient way of doing that would be centralize those numbers into one phone number that could be contacted. And Google Voice is a good example of allowing you to do that. So I have a cell, I have an office, I have another phone. Well, what I'm able to do with that is create one Google Voice number, give that Google Voice number out, and when they dial that number, it rings all of my devices. And this way, you're assured of getting to a phone that I'm at, if it's with me. It's just a more efficient way of giving out a phone number, or a more efficient way of you contacting me if you need me. So route summarization, that analogy may be a little off. It's close to what we're attempting to do with route summarization. We're attempting to take all these different networks, right, all these different routes, and advertise them out to the other parts of the network as one route. So how do we do it? Well, what we're going to do right now is take these 4 network segments and we're going to walk through the steps of summarizing them. As you can see, they've been summarized in this diagram. Well, let's see how we do. They're all default /24 networks, and the first thing we have to do to discover how to summarize these routes is break them into their binary format. Here they are in their binary format. The next step is to find all the like bits. Right? As we can see, if we start here, we have all ones, all zeros. What we want to find is the last vertical line that matches. So we highlight them in red just so we can see them a little bit clearer. And if we scroll down here, we see right at this bit right here is the last bit that matches. After that, we have 0, 0, 1, 1. So we're looking for all ones and all zeros. Now that we know that, what we want to do is count up those bits and see what the mask is going to be. Well, if we look at that, we have 8 plus 8, 16, 17, 18, 19, 20, 21, 22. So our new summarized mask is going to be /22. We're going to replace /24 with /22. And how we do that, and this is the important part, you take the first network, the very first network, so in this case it was 4, and we append it with the /22, and that's the network that we advertise out. So that's a basic, simple method for finding how to summarize a network. It's tedious, but it's easy. I agree. Breaking out the bits can be very tedious. But to make it quicker, right, we're looking for the octet of interest, where the numbers are changing. So you don't have to write out all of these, and we're really not interested in this octet either. We're only interested in the octet where the numbers are different. So 4, 5, 6, 7, the third octet is the octet of interest. So in reality, you could just break out that octet and use the same method to find the summary route. Let's try another one. Here's a class B, and we have a lot more routes to summarize. Once again, it's not difficult. Just use the method that you've learned in the first part. Look for the octet of interest, the one where we see the changing taking place. That, in this case, is the third octet. We're going to look at that and break it out into its binary format. So once again, here it is broken out into its binary format. We could have just broken out the third octet. That would have worked also. Next, we find all the like bits. We're interested where the bits are changing. And in this case, if we look right down here, we see it goes 0, 1, which means this is where the binary numbers are changing. Everything else before that is the same. We're going to advertise this network out as a /19. Once again, what's the rule? It's always the first network number. So in this case, 171.168.2.0 is the first network. We'll summarize our mask and advertise out that number to the network. It may not always be possible to summarize all the routes into one. You may have to, at times, break it into 2 or 3 summarized routes, depending on the size and complexity of your network. But this is a good way and the best method for summarizing routes. There is a PDF that has some practice exercises that you can go through to practice these skills.